Hi, Charles. Can you hear me?
Yeah, hi, Professor. Yes, I can hear you.
Uh, Hold a second. I can't hear you. Output. Hmm. Hello, can you hear me?
Yeah, I could hear you.
Oh, okay, great. I can hear you too. Okay, great, great. Okay. So for some reason, I have my desktop died down. I can't use my desktop, so that's a bummer. Uh, so now trying to make uh my laptop work. Dismiss this. Okay. Okay, so let's wait for 1 more minute before we get started. And I do have some technical issues here. My desktop just died. Um, I have all my files on my desktop. So now I have to migrate everything into my laptop. I honestly don't know whether the program will run here because I haven't tested the environment, but we'll try. We'll see how it goes. So let me close this and to find my files. Uh, okay, so let's get started. Good morning or good evening, everyone, depending on your time zone. So this is our very last AI interest group meeting in this semester. So over the semester, we have accomplished a lot. Several of you have made great presentations, and we will continue our AI interest group in the coming semester. But even during the summer, if you have some wonderful materials that you want to share with the group, feel free to let Yu and myself know. And we'll also recycle some of my previous talks in the open classrooms and upload some of the talks to the YouTube channel to entertain our subscribers. Um, and if you have something to share, say, if you've done a presentation somewhere regarding AI that you take pride in, or you want to record some new materials for our AI interest group, feel free to let you and I know. We are more than glad to incorporate your talk and share with the community. So you may hear some background playing. That is my younger son, older son, that practicing piano. They are going to have a class soon, so they have to practice tonight. So I apologize for the background, sound. Um, and in the previous session, actually 2 sessions ago, if you remember, Zach offered us a fantastic, really fantastic overview or introduction to genetic algorithms. And we all learned a lot. And given, since his lecture, I self-learned a little bit about genetic algorithms. And by no means, I'm an expert on that. I'm still a very a starter, I would say, a newcomer to this fantastic domain. But I feel urged to share what I learned with you, including some of the the lecture, the presentation slides, providing you an overview of the genetic algorithms together with some of the experiment I have, and basically providing you some templates to help you get started. So as long as I would say you have basic Python programming skills and you learn the fundamentals to genetic algorithm, a lot more is just a formulation of the task at hand you want to solve. So we will come to that point a little later. Well, I don't know whether Zach, are you here? Or maybe not. If you have some questions I cannot answer, no, I will pass that to Zach later on. So no, I think the really we are pushing our own boundaries here, and we try to learn something new, and then we can help each other. Okay, so that is the sole purpose of this AI interest group. Okay, so let's get started. Let me share my screen again. I may have some difficulty in the presentation and the demonstration because I just switched to my laptop. So bear with me if there's any technical difficulties. And also feel free to ask your questions, although I may not be able to answer all of them because myself is very new to this field. But just feel free to let me know, post a question or just unmute and talk. Okay, so let me share the presentation slide for today. It's going to be a very brief overview of what I have learned about the algorithm. Okay. So you can you see my presentation slide?
Yes.
Okay, great. Okay, so as the title suggests, it's a very gentle introduction to genetic algorithms with Python and DEAP. The reason I choose DEAP because there are a number of genetic algorithm Python modules, but DEAP is probably the most popular and also very much standardized. So you can use DEAP and customize it to solve many different genetic algorithms. And no genetic. So in Zach's session, he used the word of evolutionary algorithms, and genetic algorithm and evolution algorithm are almost the same. Although my understanding is the genetic algorithm is more specific. So besides genetic algorithm, there are potentially other evolutionary algorithms there, I would say the genetic algorithm probably is the most widely used evolutionary algorithms. So here we just use the two terms interchangeably. Okay. So first, where the genetic algorithm come from? It comes from the Darwinian's evolution theory that all of you are familiar with. And the algorithm is based on three very simple but powerful principles. The first one is variation. So we believe that the population, it doesn't really matter whether it's a human population or animal or algorithms. So the variations among the individuals are very diverse because the genetic composition are different. So there are a lot of variations among the same population across different individuals. And then the second principle is inheritance. So the offsprings of the individuals will be able to inherit some properties, basically the chromosomes from their parents. Okay? And some of the properties in this inheritance are beneficial to the survival of the offsprings. And the third principle is that probably the most popular, the most famous one, that is the survival of the fittest. So the offsprings that with certain inheritance are more likely to survive compared to others, by the nature or by some selection criteria. Okay. So those are the three basic principles for Darwinian evolution. So based on those principles, we could consider some genotype. So genotype here, of course, is not the same as the biological genotype. Here, we make it really simple. It just means that each individual, or we'll say, each algorithm or model is represented by a chromosome representing a collection of genes. Okay, so we could consider, each chromosome could be represented here by a binary string, basically taking value of either 0 or 1. And here the chromosome contains how many? 1, 2, 3, 4, 5, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 different genes. Okay, so each gene is represented by a binary string, a binary number, either 0 or 1. And this chromosome consists of 10 different genes. Okay. Of course, the algorithm can also contain, besides binary string, it can contain integers, for example, 0 to 10, or it can even contain continuous variables. Okay, so it won't have to be a binary string, but binary string is the simplest one. Okay, so that is the genotype. And then consider each individual represented by the chromosome, right? So therefore, we can form a population of individuals, basically a population of different chromosomes. So here we have 5 individuals or 5 chromosomes. And as you can see that the population is diverse, right? Because it contains 5 individuals, and each one has a different set of genes. Okay, and then the fitness function, right, which is another key component to the the algorithm. So the fitness function is a function we want to optimize or the problem we want to solve. Okay, so basically, we use the fitness function to score each individual chromosome, and some chromosome are going to have a higher score. Other chromosomes are going to have a lower score, based on the fitness function. And then the selection process is that the individuals who score higher in the fitness function are more likely to be selected and reproduce. Reproduce just means replicate itself into the next generation, whereas the individuals score lower would have a lower probability to be selected and reproduce. So it means that those individuals who score lower are more likely to be eliminated. Okay, so without having the capacity to reproduce itself. Okay, so that is the fitness function. The fitness function can be mathematical or it can be heuristic. It won't have to be represented by an explicit mathematical function. Okay. Okay. And let me know if you have any questions. Just feel free to unmute yourself, or you can post your question to the chat and we can go over them. Okay. Something's wrong with my hand advance. Is this one? No. Next. Okay. Okay, and then the selection. Selection just means, after we apply the fitness function and we calculate the score for each individual, then we'll use some methods, some selection method to select the individuals, and those individuals are going to reproduce themselves and create the offspring to form the next generation. Okay. So there are many the selection method that we are going to talk about. Okay. So after selection, there's a suite of method crossover. So crossover means the selected individuals or the selected chromosomes are going to go through some exchange process. Okay, consider this is the in biological being, this is mimicking the mating process, right? Because, well, we are going to pair two individuals or two chromosomes to produce their offspring. Okay, and here we have a very simple chromosome exchange process in which we have a single cut of the data. Okay, so if you see that on the upper side of this image, we have a cut point at the fifth digit, right? So at the fifth digit, for both chromosomes in the pair, we exchange their values, okay? So that the last four values in the first chromosome and the last four values in the second chromosome are exchanged, okay, to produce their offspring. Okay, so this is called crossover because the genes got exchanged in that crossover method. Okay. And after the crossover, we also have mutation. Okay, so mutation is pertaining to a single chromosome. Okay, not a pair of chromosomes. So after the algorithm, the chromosome produces offspring through the crossover. Each chromosome is able to is having a probability of introduce some new patterns. Okay, there are of course different mutation methods, and here a simple one is we have a random flip. Okay, so flipping means it's like flipping a coin that each gene in the chromosome has a certain probability of being flipped. Okay, so here we see that the one in position 6 is switched is selected and flipped to 0. Okay, whereas all the other genes in the chromosome stay the same. Okay, so that is one of the several popular mutation method we are going to introduce. Okay. Okay. And this just a recap of the basic flow of the genetic algorithm. Okay. And this follow a chronological order. Okay. From the start, we first create or generate the initial population. Okay. So we start with an individual, basically a single set of chromosome, and then we create an initial population, usually randomly. Okay, and then we calculate the fitness for each individual in the population, based on the fitness function that we created. Okay. And subsequently, using the fitness score, we start to select, pairs of chromosomes to be reproduced. Okay, and the reproduction process is started with crossover. Okay, remember that we need two chromosomes to mate. Okay, exchange their chromosome, part of this chromosome, their genes, and then each individual, each chromosome is also go through a mutation process, okay, such as random flip. And then after that, after the mutation, we recalculate the fitness for each individual in the population. Okay, so this process, is done for all the offsprings of the first generation. Okay? And then we iterate this process from selection to crossover to mutation, and then calculate the fitness scores for each offspring until a stop condition is met. Okay, if the stop condition is not met, we just continue the selection crossover mutation process. But when the stopping condition is met, we will stop. Okay, so after stopping, we'll be able to choose the chromosome or individuals with the highest fitness value. We call it Hall of Fame. So basically, those achieving the highest fitness scores are going to be preserved, and then we use that Hall of Fame individual or individuals as the best outcome, as the best solution to the question. Okay, so that is the basic flow of the genetic algorithm. And then you may ask, what are the stopping conditions, right? So usually, there are three different stopping conditions, and as long as one is met, we will stop the reproduction selection process. The first condition is time eclipsed. Say you set up a fixed time. Say I want to run this this algorithm for say 5 minutes, for an hour, depending on the complexity of the question. But when the time is met, you will stop the algorithm regardless of the outcome. Okay. The second condition might be the overall cost. Because, well, if you run the algorithm in your computer, it consumes CPU, time, and memory, right? And of course, associated with the cost, you say, well, I'm not only going to use, I don't know, maybe 15 minutes of CPU time, or I'm only going to consume that much memory for that long. And then you can, of course, decide upon when you will need to stop. And the third is your solution is you achieve a solution that is better than some preset threshold, right? So say that I want the algorithm is about say achieving a value greater than 100, right? So when the algorithm has found a solution to give you a value that is above 100, then it will say, well, this is good enough, right? I'm going to stop it, right? So usually it's one of the three stopping conditions. Okay. Any question? Okay, good. Okay, and then let's talk more about the selection method, right? So we talk about selection method, and then we move on to the crossover method, and then the mutation method, okay? Because there are several popular methods for each for you to choose from. So the simplest selection method, and probably one of the most widely used, is the roulette wheel selection, or it called fitness proportionate selection. So Zach in the previous session introduced this method in some detail. So it's very easy to understand. Say we have individuals A, B, C, D, E, F, and each has a fitness score calculated. And then we just add up all the fitness scores, and then we use the individual fitness divided by the total fitness score to get a proportion. And of course, all the proportions add up to 100, right? So, and then consider that you have a roulette wheel that is going to spin, and spin, of course, randomly. So, and each pie in the wheel represent the proportion occupied by each individual. Okay. So, for example, the fitness score of A is 8, and it consists of only 7% of the total fitness scores. Whereas, say E, the fitness score is 45, and occupy 40% of the portion. So when you randomly spin the wheel, of course, the probability of landing on E is going to be a lot more than landing on A, right? So that it'll be several times higher than the probability of landing on A. Okay, so therefore, the roulette wheel selection actually is because it's proportional to the fitness score. The individuals with higher fitness scores are much more likely actually to be selected than the individual with a lower score. Okay. Okay. And the second algorithm for selection is called stochastic universal sampling. This is really similar to roulette wheel, but the difference is that all the individuals are chosen at the same time. Okay. The representations are the same, okay, but you don't spin the wheel multiple times and each time select an individual. You spin the wheel only once and then you just take a look of the individuals that fall into each of the regions. Okay, so and then of course the individual would distribute evenly right across the surface of the wheel. Okay, so compared to the roulette wheel spinning, the stochastic universal sampling offer more chances for those with lower fitness scores. So they have a higher chance to be selected compared to roulette wheel spinning. Okay. So that is the difference. And of course, using stochastic universal sampling is faster because you only need to choose all the individuals by spinning it once rather than repeating the process for the number of the overall sample size you want to achieve, the population sample size you want to achieve. Okay. Any questions so far? Okay. And the third selection method is called rank-based selection. In the rank-based selection, you first calculate the fitness scores for each individual, and then you rank them. So the individual with the lowest fitness score ranked 1, and the individual with the highest score ranked the last. Okay. So here we have 6 individuals in total. So individual E, which has the highest fitness score of 45, ranked the 6th place. Okay. And then you calculate the relative proportion based on the ranking rather than based on the fitness score. Okay. So it means that to calculate the portion for A, that would be 2 divided by 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay. So that is the calculation of the relative portion for rank-based selection. And as you can see, the rank-based selection give individuals more of an equal chance to be selected compared to the roulette wheel selection. Right? Because well, if you take a look of the A and E, previously in the roulette-based selection, A occupied 7%, E occupied 45%, whereas in the rank-based selection, A occupied 9% and E occupied only 29%. Right? So the rank-based selection offered individuals with lower scores more of a chance compared to roulette wheel selection. Any questions so far? Okay. Besides them, there is another selection method which offer you more flexibility that you can play around with the numbers. It's called the fitness scaling method. Okay. So the fitness scaling method is driven by two parameters, A and B. And the formula is the scaled fitness score equals A times the raw fitness score plus B. Okay, and A and B are the two values that you can assign. Okay, so say you have the raw fitness value for individual A is say 4, and the raw fitness score for individual B is 45. And their respective assigned or scaled fitnesses are 50 and 100 respectively. In this case, of course, you can solve A and B, and you'll be able to calculate A equals 1.22 and B equals 45.12. Okay. And then of course, the scaled fitness will be just equal to the 1.22 times the raw fitness plus 45. Okay. So as you can see from the formula here, when the B is much greater than A, you would create two individuals that share similar fitness scores. Whereas if the A dominate B, and then the two scores would be dramatically different, right? So basically, you can use the values of A B pair to determine how similar, how different the two fitness scores between the two individuals or more individuals. Okay. So that is the fitness scaling. Any questions so far?
Yeah, the question.
Yeah.
So the fitness scaling is for calculate the difference. Is that what you mean? If we know the A and B, we can define how different two individuals is. Is that the only function of fitness scaling?
So this is a demonstration of if you know the scaled fitness, you can solve A and B. But usually when you use fitness scaling, my understanding is that you assign the values for A and B upfront, and then you use that A-B pair to scale the raw fitness scores.
So why we need to like compute the raw fitness score to the scaled fitness score?
The reason is, consider this is a good question and actually pretty profound question. So, of course, nothing prevent you but just using the raw fitness score, right? And actually, you could consider the rank-based the previous we talked about the rank-based selection as well as the stochastic universal sampling. They are actually modifications of the raw fitness score, right? Using different ways to scale the raw fitness score. And the fitness scaling is just another way to modify the raw fitness score. It is because there's always a trade-off, regarding how much exposure you want the individuals to be exposed to when how likely they want to be selected. So if you only select the fitness, the most fitness individual, then you will lose the diversity of the population, right? So if this individual fail, your entire experiment algorithm would fail, right? On the other hand, if you want to keep most of the very weak performers, right, individuals with low fitness score, then the algorithm may take a really long time to run, right, and may not be able to identify the optimal solutions. They may probably stuck in some local minimum or or a local maximum rather than achieving the global minimum or maximum. Okay. But of course, you don't know, right, beforehand, because, well, we are trying to identify the solution in a very high dimensional space. Okay. So usually you want to experiment with different different selection method to see which one give you a better outcome. Of course, it's very much task driven. Okay. So therefore, a lot of time you may or may not use the raw fitness scores. You want to do some modifications. So for example, if I want to be conservative, right? I want to keep the diversity of the population. So I want to intentionally keep a lot of weak performers because, well, you would never tell, right? Some of the weak performers may on the long run deliver strong offsprings, right? So if you want to keep that property open, you would set A score to be small, but B score to be large, right? In this case, you would make the selection more equal between the high performers and low performers. On the other hand, say, if the problem is relatively simple, I'm pretty sure that the best performers are going to win anyway. In this case, I would make the A very large and B quite small, so that you are even exaggerating the difference between the weak performers and low and strong performers. So strong performer becomes stronger and more likely to be selected compared to weak performers. In this case, the population you create are going to converge really quickly, right?
Thank you.
Great question. Any other questions? Okay, so presumably I don't really offer you the the best explanation possible, but well, I'm trying my best. Okay, so here is an example of the fitness scaling. Using the previous score of A equals 1.2 and B equals 45, and then as you can see that the selection of A and B pair make the relative portions between the 6 individuals much more similar to each other, right? Much similar to each other compared to their raw fitness scores. Right? Okay. And finally, another very popular selection tool is called tournament selection. That was the selection method that was introduced by Zach. And tournament selection is really simple. It doesn't even require a mathematical function. Every time among all the individuals, I'm going to choose say 2 or 3 or 4, the number you can choose. You can decide how many individuals you choose to compete with each other. And here, for example, we have 6 individuals and I choose 3 of them. A, B, and F, and then I make a comparison. I will say, well, whoever has the highest fitness score is going to survive. In this case, F is going to survive because F has a fitness score of 17, and A and B are eliminated. Okay. And you can do the same for the entire population, so that you can choose a desired number of individuals to reproduce. Right. And think about this. This is a very interesting selection method that if you choose more individuals to compete at the same time, the outcome would be more homogeneous, right? Whereas if you choose less individuals, if you choose 2 individuals instead of 3 to enter competition, and then the diversity is going to be in the population is going to be higher, right? So take a moment if it is puzzling to you. Think about what is the difference between 2 and 3. Okay. So because, well, if you only choose 2 individuals, you are going to introduce more randomness, right, to the outcome. Whereas, for example, an extreme case would be that you choose only 1. the first place among all the entire population, right? In this case, you end up with a completely homogeneous individual, which only one individual is allowed to produce the offsprings, right? That would be a completely homogeneous population example, right? So therefore, the tournament selection is very much dependent, the selection outcome is very much dependent upon the number of individuals that are selected simultaneously to enter the competition. Any question? Okay. And now let's talk about different crossover methods. There are a few crossover methods that are really popular. The first one that you've already seen is the single point crossover. Okay. The single point crossover is consider you have chosen a pair of chromosomes and you decide upon a single cutoff point, right? So with a single cutoff point, you are going to cut the chromosome into two parts, right? For both chromosomes at the same place, okay? And then you will say, well, I'm going to exchange the chromosome, the tail of the chromosome between these two. Okay. So therefore, if you take a look, in the first chromosome, the last four digits are 1010. And in the second chromosome, the four genes in the tail is 0010, right? So these two four-digit numbers are switched and add to their respective chromosome. So this is called crossover. It's mimicking the mating process in the biological beings. Any question? Okay. And as you can guess, besides single point crossover, we can extend that definition to 2 points or k-point crossover. So here we show the 2-point crossover, in which you have two counterpoint. The first counterpoint is at digit 3, and the second counterpoint is at the digit 7, right? So in this case, what is the chromosome in between the two the two counterpoints are exchanged? Okay, so the first in the first chromosome we have 1110 in between the two counterpoints, and that is exchanged with the 1100 in the second chromosome. Okay. You can extend this idea to more than two counterpoints. Okay. And then another crossover method is called uniform crossover. So in the uniform crossover, you randomly select a fixed number of genes, and then you just switch them, okay, across between these two chromosomes. Right? So you randomly select some indexes, right? So here we randomly select a number of indexes of the first chromosome, and then we'll decide, well, for those chromosomes, we are going to exchange the numbers, the genes at the same location, between the two chromosomes. Okay. And we also have the ordered crossover. So the ordered crossover, aims to preserve some of the location, or we say the sequence of the chromosome, right? Because consider that human genes, the DNAs, that the sequencing is important, right? Because it represents some functionalities, right? So here we try to preserve the order of the chromosome, of the genes in a particular chromosome, right? It's not a complete representation. The algorithm actually is follow a number of steps, but here I just want to showcase that this order crossover method try to preserve the ordering of the genes. Okay. No, I can give you the reference if you want to know more about how the order crossover is done, but I think it is an overkill. Okay. And finally, let's talk about the mutation method, right? There are a number of mutation methods that are commonly applied. The first one is flip bit mutation, which is simplest. Flip bit mutation says that, well, across all the genes in the chromosome, they have a probability of being flipped, okay? The value being flipped. So here in position 4, that 1 is flipped to 0. Okay. So the flipping is not bounded, is not constrained by the binary gene. It could be integers, and likely it's going to be possible for continuous variables. But no, I haven't learned about that, so I can't really claim. But I know that is definitely extend to integer. So randomly select, say, one number out of 9 eligible numbers. Okay. And the SWAP mutation is a different idea. SWAP mutation means that, well, among the genes in the chromosome, the values have a probability, the genes have a probability of being swapped place from each other. So in this case, the 3 and 6 are flipped, right? So the order is flipped. So 6 takes the place of 3, and the 3 takes place of 6. Okay, so that is called swap mutation. Any questions so far? Okay. And inverse mutation, a very simple idea that we randomly select a number of genes from the chromosome to reverse the ordering. Okay, so the previous chromosome has 3, 4, 5, 6, which are selected, and the orders are reversed. So now it become 6, 5, 4, and 3. Okay. And we also have scramble mutation, which take a similar, a little bit different idea to say, well, among a sequence of genes in the chromosome, we are going to randomly order them. Okay. So here, we have genes 3, 4, 5, 6 selected, and the random order becomes 4, 6, 3, 5. Okay. So we have introduced a number of selection method, crossover method, as well as mutation methods. And before we move on to the lab session, I want to talk a little bit about the elitism, which actually introduced by Zach in his presentation. And elitism basically is a strategy to retain the best individuals in the population of the genetic algorithm, okay, across generations. Okay? Because remember, when we apply the selection method, even the best performing individuals, the individuals with highest fitness scores, has a probability of being eliminated, right? Because every selection is driven by probability. Even individuals that has a score, a relative portion of 90% has a 10% chance of being eliminated, right? But well, if you are confident that those best performing individuals actually should be preserved, remember in the Zach example, he talked about the horse racing, right? To probably all of our surprise that over the last 300 years, the auto racing horses have come from the descendants of the first generation, the 2 horses, right? So that is probably a classic example of elitism, right? So regardless of the selection method, if we want to retain the best performing individuals, then we can apply the elitism. Right? So the purpose, of course, is to prevent loss of the best found solutions. Right? and it will ensure consistent improvement in solution quality over time. But of course, no, that is the aim, not necessarily going to be the case. Okay. And to implement the elitism is actually pretty simple, right? So you just need to select the top performing individuals and you directly copy them into the next generation. You do not actually allow the selection algorithm to touch those best performing individuals. Okay, so it means that they have no a special path, right? You consider, right? So they are not going to be even go through the selection process. They are guaranteed to have the opportunity to produce their offspring. Right? I guess probably you can find some examples in human history as well, but that is out of the scope of this discussion. Right? Any question? Okay, so we are pretty fast in terms of I forgot to mention a few things about the DEAP before we go into the lab session. So as we said, the DEAP is a very versatile Python library for evolutionary or especially genetic algorithms. It has a few key features, very easy to use, highly customizable, and provide also the ways that you can customize different genetic operators. Okay, so you can use the default algorithm, which is pretty good, that I'm going to show you how to use them. But down the road, if we want to dig deeper, we can also customize some of the basic operators or probably implement our own operators, although I'm not at that stage. Okay, so I'll use the program as it is. And we can install, of course, using the pip install deep. And then usually there are a few steps. We are going to see this play a role again and again. Those are the common steps that all the genetic algorithms go through. First, we need to define fitness and individuals. We create fitness. And usually you need to decide whether you are going to create, you are going to evaluate based on the highest fitness score or the lowest, right? Basically, are you expect the individuals to maximize or to minimize the fitness scores? Okay. Of course, that is the task driven, really depending on what you want to accomplish, right? So if you want to maximize the fitness score, you specify fitness max, and then you assign the weight as usually as 1.0. So 1 is being positive. It means that, well, I'm going to maximize the fitness score. Whereas if you set weight equals -1, it means that you are going to evaluate based on the smallest fitness score. The smaller, the better. Okay, in this case, you have fitness min. Okay, and probably in some applications, you can set a number of weights rather than single weights, and you can set the weights less than 0 or greater than less than 1 greater than 0. But well, no, I don't have examples for that yet. Maybe later on when I learn more, I'll be able to show some cases when the weights would not be equal to 1 or -1. Okay, but here for the cases we are considering the weight is either 1 or -1, denoting whether you are calculating a max fitness score or a min fitness score. And the second step is to define individuals. You create an individual, and individual, of course, is going to be some kind of list, usually array or list. Because remember, each individual is a chromosome, right? A chromosome contains a list or an array of numbers, right? Whether it is a binary number or integers or continuous numbers, they are usually an array of numbers. And the third step is to register the components with the toolbox. Okay, the toolbox is coming, as the name suggests, coming out of the built-in toolbox, right? But you need to register your individuals and populations so that they can be associated with the toolbox. So later on, you can use the algorithm in the toolbox to manipulate the individual and population. Okay. And the next step is to define the evaluation function. That really is task specific. What evaluation function you want to apply, right? So that is pertaining to how you calculate the fitness, how you design the fitness function to calculate the fitness score. Okay. And then you register the evaluation function so that you can use the genetic algorithms, the selection, the crossover, and the mutation functions on those registered evaluation function. Okay. So there are a number of selection method, crossover method, and mutation method you can use out of the box. So here we show you, three of them. For the select, we use the tournament selection method called the cell tournament. For the crossover in toolbox is called mate. Here we use the 2-point crossover method. And for mutation, we use multiple flip bit. Multiple flip bit is basically you simultaneously flip more than one genes. Okay. And then finally is to execute the algorithm. Execution, you need to define the population size. So here I define population size equals 300. And then I'm using, again, the beauty method of called algorithm.ea simple. Okay. So EA simple is what I know of. There are a few other more complicated algorithms I have not tried, but usually the EA simple should be the one as the default. You provide your defined population, the toolbox, and then you decide upon some probabilities, including the probabilities for crossover and the probability for mutation. And also you define how many generations, basically how many offsprings you want to produce. Okay, so you want to produce 40 generations, and then you just run the algorithm. Usually the algorithm run for the simple questions that we experiment with are really fast. Okay, take probably a few seconds to run. But of course, it's driven by the sample size and by the how complex the evaluation function is. Okay, so just that is the overview of the algorithms, and now let's take a look of the Python implementation. So let me take a moment to okay, to find so I'm sharing my screen now. Okay, so let me first take a look of the knapsack problem. Okay, hopefully it can run because I actually run this with my another machine, not this one. So really, what I want to talk about is not go into detail of the programming side, but I want to show you how we think about the problem. I think that is the interesting part of this DEAP algorithm. Okay, so here, as you can see, that we have two files, right? We have the knapsack py and also the knapsack solution py. The knapsack problem is a very, I would say, introductory evolutionary or genetic algorithm, and to solve the question of, well, we have different items we want to put in the knapsack, right? And each item has a different value and also has a different weight. Okay, for example, a map has a weight of maybe 0.1 pound with a value of 9. And you have an umbrella which has a value of 6 and a weight of probably 1 pound, right? So each item has a specific value and also specific weight. And the goal is to maximize the total value of the items you put in the knapsack without exceeding the limit of how much the knapsack can contain. For example, if the knapsack can only contain up to 400 pounds, then given that you do not exceed 400 pounds, you want to maximize the values, the total values of the items put in the knapsack. Okay, so that is the optimization problem we try to solve here. To think about this problem, usually what is hard, as I found out by implementing this, is not to implement the algorithm, because, well, the DEAP the DEAP module has very much standardized all the functions you could use as we showcase, right? How to create individuals, the population, how to use the different selection, mutation, crossover tools, right? So this is very much standardized. But the key is for you to represent the knapsack problem and to create a Python class to contain the task, right, to define the task. So that is probably the conceptualization of the problem which take the center stage. Okay. So it took me some time to read some textbook chapters and tutorials to figure out a relatively, I would say, standardized way to solve this. Okay. Usually you want to have two files. The first file is to define the problem at hand. The second file is just to apply the DEAP module to solve the problem. Okay, so therefore, actually, the knapsack solution here contains the DEAP implementation, which is very much standardized. You only probably need to do minor tweaks or changes to solve the question. But what I think is more conceptually challenging is the representation of the knapsack problem or other the problems. Okay. So for the time being, we have limited time, so we'll probably mainly go over the conceptualization, which I feel is more probably beneficial. Okay. So as we said, we need to build a class to represent the knapsack problem. So I built a Python class. For those of you who are not familiar with Python class, so building class in Python is to create an object, because Python is an object-oriented language. Everything is an object. So here we are creating an object called knapsack. Okay. Usually when you create a class, you first need to use the standard init to define the class, right? And then you create some method that work with the class. Okay, so therefore I first create the standard init to define the class. And here you need to think about, well, what are the key essential things I want to put there, right? So here, what I said, well, I need to, because the goal is to maximize the capacity of the knapsack. So I set the max capacity at the starting point to be 0, right? And later on, we can maximize that. And then we also need to have a number of items to put, right, in the knapsack. So here is also, we initialize just an empty list to contain the items. And then, of course, we need to get data, right? So here we set a function called init data. So this is going to get the data we need. And the data would be just a list, consider as a dictionary of the containing the name of the item, the value, and the weight of the item. Okay? And we have a number of items to choose from. Okay? So this is just the init, the standard init function. And usually we need to know how many items are there, right? So here I just create a len function, a standard len function. And len function is nothing more than just count the number of items in the items list. Okay. And then we can initiate the data. The data is very simple. As we said, this is just a dictionary or a list of tuples containing the name of each item and the corresponding weight, okay, and then the value. Okay, so we have a number of items here, right, with different value weight pair. And then here we can set the maximum capacity of the knapsack to be 400, right? So 400 is the max. We cannot exceed that 400 total weight. And here we create a function to calculate the value, right? Because we need to know this is the fitness function, right? We need to know the total value because we want to maximize the total value, right? So we need to have a function to calculate the total value. And the total value is pretty simple to calculate, right? First, we start with 0 as the total value and total weight because we haven't put anything there yet. So the total weight equals 0, total value equals 0. And then here, we just go through the list. So the list here, we call it 0, 1 list. This will be provided as the input. 0, 1 list, as you can imagine, is just a list of 0 and 1s. So if we include a certain item, we will have 1. Otherwise, we'll have 0. Okay. So that list basically is going to decide which item to put in the list in the knapsack. What items are going to be left out. Okay. So this is the 0, 1 list. Okay. And we just go through this 0, 1 list. And we get the item weight and the value from the items. Okay. So we just keep adding the total weight plus the new item we add in. So as long as this is less than the specified maximum weight, which is 400, we'll just keep adding, right? The total weight would be the total weight would be the 0, 1 list times weight, right? So if this value is 0, we don't add anything, right? If this is 1, we just add the weight of that item, right? And then the total value the same, right? We add the value to the total value, we add the weight to the total weight, and then we return the total value. Okay. So through this simple loop, we'll be able to calculate the total value and the total weight for any specific 0, 1 list. Okay. And then, so this is the function to print the selected items in the list, right? Because we want to visually see what is included, what is not included. So this is the function is the same as this function, but no, here we just want to print. So every single time we go through this will say, I'm adding this, the weight is this, and the value is that, the cumulative weight, the cumulative value as well. Okay, but only for those things who are added. So therefore, only when the item in the 0, 1 list is equal to 1, we are going to print this. Okay, if it's 0, we just skip that. Okay. So yeah, so this is the entire class. No, this is of course not the only way to solve it. There are many potential ways, but usually we start with the representation of this question in a class. Okay, so again, let's recap what we learned. First, we use standard init to initiate this class. And then we create a function to return the number of items in the list. And then we provide the entire data. Okay. And after that, we create a function to calculate the total weight and value from this, from all the items placed in the knapsack. And really importantly, what we try to calculate later on, we try to optimize is just this 0, 1 list, right? Because we want to know what item to put in the knapsack, what item should be left out. And so this function is not is optional, but is informative because we want to know what are the items put there, what items are left out. So each time the item add how much weight and how much value to the total value and total weight. Okay. And after that, you usually want to test your class, right? You here you initiate the class, and then you can create a random list. So this random list is just 0, 1 values. Okay. And then you can use the print item function to print this random list to see whether it showed how to add items. And then, of course, you can get a total value of the items used to get total value function. Okay. So if we run this, Python knapsack py, you see that in the terminal, it show you this, right? So this is a random list we created, a bunch of 0 and 1 denoting exclusion or inclusion of the item. And then here we said, well, because this is 1, we are adding the compass. Compass is the second item. And then the fourth item is sandwich. We add sandwich, we add banana, etc. And now actually we adding all the weight. The weight is only 196, and the total value is only 510. Okay. And of course, because this is a random list, so it is far from optimal, right? As you can see that the weight is far less than 400, so we can actually have a lot more value than 510, but that is just showcase a random solution. Okay. Okay, so as long as we can formulate that, we can go to the knapsack solution. Let's see how much time we have. Okay, we still have some time. So here we in the knapsack solution, we first create an instance of the standard problem. Remember, we create that in this knapsack py file. Okay. And here are just some problem constraint, right? So very much you can borrow the same code for the entire file knapsack solution. You only need to do some slight modifications to solve a different problem. But of course, this problem have to be discrete problem. Okay, it's not able to solve continuous problems. I haven't really learned how to solve continuous genetic algorithm yet, but well, probably that's a good learning opportunity in summer. So we define the problem constraint. So this is the item length, basically how many items in the knapsack, the population size. So all those parameters you can experiment with. Okay, remember the population size. The larger population size, the more diverse, and it's going to take longer for problem to run. This is probability of crossover. Okay, so 0.9, 90% of the population goes through the crossover. Okay, it means that 10% will not do the crossover. They're going to directly pass. Okay, and mutation. So this is the property of mutation. So this 0.1 actually it means that 10% of the offsprings after crossover will be selected for mutation. Okay, so they are at the individual level, not at the gene level. Okay, so make sure that you get that, because later on we are going to define another probability for mutation, which is for at the gene level. Okay, so this is at the individual or chromosome level. Okay. And max generations, how many generations we want to run? We want to run 50 generations, and we want to keep 10 individuals in the Hall of Fame. So those 10 individuals with the highest score, fitness score. Okay. So this is a random seed. This is completely optional. And here we create a 0 or 1 operator. Why we need 0 or 1? Well, no, because this is a binary outcome. You only have either 0 or 1 as for one gene, you have either 0 or 1. Okay. After that, I create a fitness class. Remember that because we are maximizing the value, right? So therefore, the fitness class is weight equals 1. If you are minimizing, you set a weight to be -1. And here I create an individual based using the fitness the fitness class we just defined. And then we can register the individual. So that we use this to create, so this is a class we create individual, okay? So how we create individuals? Well, you use the 0, 1. So 0, 1 is the function you're going to create for, every single gene is going to be either 0 or 1, right? And then you use this init repeat to repeat that the 0 or 1 process multiple times, depending on how many chromosomes you want, right? And remember, the number of chromosomes actually is the number of items, right? The total number of items in the knapsack, okay? So therefore, basically, this function is going to create a list, and the length of the list is going to be the item length. And for each item in the list is going to be either 0 or 1, okay? Because you apply this 0, 1 function, right? Okay, and after that, you have an individual. Of course, you can create a population, right? You just repeat this many times, okay? And this is called a list because you have a list of individuals, okay? And after that, you evaluate individual. How you evaluate that? Well, this is you evaluate it, right? This is the get total value, right? This is the function you created. Because you are going to judge individual performance, based on the total value of the items in the knapsack. Okay. And then you register the evaluation function. After that, those three are very much standardized. You can, of course, apply different method for select. Here we use the tournament for selection function. We use the flip one. We use the single the single point for the crossover called mate, and we use multiple flip bit as the mutation function. Okay, you can choose different one. So here the tournament size is 3. So basically 3 chromosomes are going to be chosen to compete with each other. And for this probability, this 1 divided by item length. So this is the probability for each gene to be mutated. Okay, so this probably pertaining to at the gene level, whereas the P mutation is pertaining to individual level. Okay, so make sure that you can differentiate these two probabilities, and both pertaining to the mutation process. And then, of course, you want to report some statistics. So here I register a statistic. So this is a built-in method. And I want to register both the max and the mean. So max would be the best performing individual score, basically the highest total value achieved by the entire population. Whereas the mean, of course, is just the average total value by the cohort. Okay. And then we create a Hall of Fame, so that because remember we retain the 10 best performing individuals. And we keep updating this list for every single generation. Okay. And then this is, remember, we use the eSimple, right, algorithm. This is a built-in algorithm. We just provide all the parameters. We build population, toolbox, functions for crossover mutation, the number of generations, the statistics. We want to produce the Hall of Fame object. So that is the algorithm. And then we print the best ever individual. So in the Hall of Fame, the items are ordered by its performance on the descendant value. So the best performing individuals are going to have values an index of 0. So therefore, we can print the best performing individual. We can return the mean X maximum values. We provide this logbook so that you can plot the mean fitness values and the max values over time across the 50 generations. We will see how the algorithm performs in producing the total value. Okay. Any questions so far? Okay. So let's run this. Python Knapsack solution UI. Okay. So as you can see, this run really fast. Okay, it's done. We have 50 generations. Let's put this here. So we have 50 generations, and as you can see that the red line is the maximum fitness score, whereas the mean is the average fitness score across the cohort. And we've already actually achieved the best outcome less than 10 iterations. Probably at the 8th or 9th generation, we've achieved the maximum already. Okay? And so it's tend to flat out. If we take a look of the best performing value, so this is best performing. So every time we have we first add a map, and then add a compass, add water, sandwich, glucose, banana, santan cream, waterproof trousers, waterproof overclothes, note case, sunglasses, sock, so that we have a total weight of 396, which is lower than 400, and with a total value of 1,030. Okay. Is this the guaranteed best outcome? No, actually, we don't know, right? But well, at least actually, no. When people analytically solve this, we do have achieved the best ever outcome, okay, which is 1,030. But if for random problem without the analytic results, we probably don't know, right? Well, of course, this is much better than the random solution, right, which is only 510. Okay, any question? Okay. Let's see whether we still have time to talk about the travelers problem. Maybe we'll leave the solution. We'll just briefly go over the representation of the traveling salesman's problem. Okay. So let me open that. But I'll share the algorithm, the Python file, so you can play around with it a little bit if you want to get a deeper understanding. So let's see. Okay, so this is a little more complicated, and actually, as you can see, the name here, we also apply the elitism to boost up the performance. Okay. So again, no, the traveler salesman's problem start with with how we define the problem. And that is the key part. Okay, I think that is probably the part that is most difficult. So as long as you can use the class to represent the problem at hand, then the DEAP module is going to very much handle the solution, the calculation for you. Okay. So, but well, I would say conceptualization of this problem is really fascinating. It's really interesting. So we don't have a lot of time, but no, I want to introduce you to an interesting data set. Let me see whether do I have the, let's see whether, okay. So this is the website. Okay, so let me go to this website. We can take a look. The traveler salesman's problem is it's a very classic problem. That in the world there are many cities, in the particular country there are many cities, right? And the question we will ask is, what is the shortest distance without going to any city twice? Okay, for a salesperson to go through all the cities in this country and then come back, right, to where he or she originally started. Okay? So we'll say, well, this is not a huge problem. It should be easy to solve. But actually, this question is notoriously difficult to solve, okay? Because you have so many different combinations, okay? So where do you start? Where do you end? And what is the path, right? If you consider all the potential options, for any pair of cities, the solution space for consideration is increasing exponentially. Okay, so it is a pretty tough mathematical problem to solve. And usually we solve them, not analytically, but through approximation. Okay. And this website, I think it's probably belong to a university. I don't really read. Maybe it's from, I don't know. Really, I can't say it's maybe I don't know, German or other language, from some European language. So it actually contains all the major cities in different countries in this world. And as you can see that, they have the key purpose of this website is to contain all the data set that you can play with to try to solve the traveling salesman problem. And they even have PhD students. They are still hiring probably postdoc and PhD students to solve some of the questions, right? So this is a very interesting website. And what we did here is basically download a relatively simple the data set from this website containing, I think, about 29 different cities. And we try to solve this traveler salesman's problem using genetic algorithms. Okay. So I know we only have 5 minutes late, 5 minutes time, so probably we won't be able to go over the entire script. But what we did basically is the first part is download the files and then create a distance matrix. Okay. So the distance matrix is just a matrix containing for any pair of two cities we create this matrix to contain their distance, their point-to-point distance. Okay. And then after that, you have to define the goal of this this task, which is to minimize, right? Not maximize, but minimize the total distance among a list of cities, right? So if this list contains the order for the traveler salesman to travel, say from city 1 to city 7 to city 6 to city 25, right? And then this function is going to calculate the total distance based on the tour, which is just a list of cities, right? And then the function will be also able to draw the tour. This is optional, but it's helpful to see the traveling path, right? And after that, after you define this class, okay, which is actually not difficult, right? Download the data, calculate the distance, and then calculate the total distance, and then draw the traveler path. And then after that, you can use the TSP solution. And if you see that this is very much the same as the previous one, I only made some minor changes. For example, this we have fitness min rather than fitness max because we are minimizing the total distance. And here we have integers rather than binary because we have 29 cities and each is assigned with a value from 0 to 28. Okay. So here we have integers as individuals, as genes rather than the binary. Okay. But besides that, usually the entire file remains really similar. Okay. So so this represents the naive solution, and the naive solution actually doesn't give you doesn't give you the optimal solution because, well, for this simple problem, the optimal solution is known. Okay, so it's a little bit far away from the final solution. So therefore, to really boost up the performance, we apply the elitism. principle, right? Elitism is pretty simple. It's just to keep the best performing individuals and do not allow it to be lost, right? So after we modified the EA simple algorithm to include elitism, and we apply the modified version of the solution, and then we'll be able to achieve the optimal solution. Okay, so it takes some time to tweak the parameters. So those are the parameters that I found that can achieve the optimal solution. Okay, but of course, well, this is probably not the only combination. Okay. Okay. So any questions so far? I will not really go over this line by line. I don't think we need to do that. I'll ask Yu to post both the presentation today as well as the Python code to the GitHub, so we all can learn later if we are interested. Any questions? Any comments? Okay, so hopefully, we all learned something. I personally learned a lot. I think this is really interesting algorithm that we seldomly discuss, right? Not in the common machine learning introduction or deep learning introduction. So, and later on, we could think of, actually, I would encourage you to think about what are the applications of the genetic algorithm to, say, public health problem, or social work problems, or any problem that you are interested in, right? Because I do believe there are a lot of potential interesting applications. One I'm thinking is if you go to a restaurant, say, there are a lot of fast food restaurants that you try to figure out a menu, right, of items that can deliver at least some nutritional value, right? But do not exceeding the total calorie, right, or total saturated fat. You can put probably multiple constraints. So based on, say, I want to keep the total calorie to be less than 650 calories, probably sugar content to be less than how many grams. But then I want the maximum value for fiber intake for, I don't know, right? The nutritious values, right? So in this case, of course, you can use other algorithm, but the genetic algorithm is probably one of the method you can apply to help you identify the set of items from a menu, right? But well, there could be other potential applications I haven't thought of, but I would encourage you to think about them. If you have a brilliant idea, let me know, and we may pursue probably a publication on that, right? So I don't think any of us have any paper written except Zach, who is an expert in this field, using genetic algorithm. Is very much underutilized, but has a lot of potential. Okay. So I'll keep exploring when I have time. I will also encourage you to explore the genetic algorithms, especially how we solve, say, continuous cases, right, which are going to be probably even more useful. Okay, so that is the end of this semester. We will not meet again in next 2 weeks because this is going to be some of you are going to graduate. If I do not see you again, actually, I cannot attend the ceremony, the commencement. Unfortunately, I'm going to be traveling again. But I wish all of you best of luck to your future career if you graduate. And of course, you are more than welcome to stay with our AI interest group. And we'll meet together in September, in early September, I guess, right? And Yu is going to keep you informed. So I wish all of you a fantastic, hopefully relaxing, but also fulfilling summer. And not to forget learning AI along the way when you go to a vacation or spending time with your family. But remember that AI is going to be with us regardless. So it's better to learn more and faster and share with our community. Okay, yeah, and thank you, everyone. We'll see each other in the start of the fall semester then. Take care. Bye.